All right, so obviously last time the big point was probably one of the most critical parts of the semester was what happened in the last topic, right? Was references. It's not like anything was really new, but it was, right? Because it was the way we were talking and thinking about these things was a little bit more explicit. So there was a huge emphasis on that, and really everything for the rest of the semester is going to follow what happened last time with references. Primitive types are still going to act the way that you're used to. But remember, the whole point is what's stored at that memory address, and when I copied over variable, what was actually in that variable. That was it, and it was critical to know. So at this point, if you're to run this code, none of this should shock you. This should all be fairly straightforward. Right? A is 5, B equals A. So you take a copy of the contents of A, which was 5, and you put it into B. Print them out, you see 5, 5. I go and modify the contents of B. Great. But it leaves the contents of A alone because A and B are independent. The only relationship they have was at a point in time they have the same value in it, but they're not connected to one another. But this, if you weren't paying attention, is going to scare you. But if you were paying attention, this is nothing. This is easy peasy. This makes perfect sense to you. Actually, wait, no, this part should be fine to everybody. I jumped ahead. This part should be fine for everybody. You have A, but what is A? Try again. What is it really? What's stored in A? A reference to a list. It's not a list. If you think list, you're wrong. You're in big trouble. It's not a list. It's a reference to a list. And so when I said B equals A, what got copied into A? A list? No, a reference. So that makes perfect sense. So now at this point, on lines 1, 2, 3, after line 3, how many lists are there? How many references are there? 2. But then on line 5, I change the contents of B. I leave A alone. On line 5, I make a new list, and then the B becomes a reference to that new list. So on line 5 and line 6, after this is run, there's 2 lists and 2 references. So everything's fine. But now this is where I thought I was going. This is where, if you think A is a list, you're screwed. Because this is going to piss you off. But how many lists are there? There's 1. There's only 1, but there's 2 references to that list. And one of those references, on line 5, we said B at index 1 become 99. So that one single list was modified. That's it. Nothing, this shouldn't shock. One single list was modified. If this concerns you, if this confuses you, you're missing the point. You clearly, maybe you fell asleep during the references lecture. Because no, this makes perfect sense. This shouldn't scare you at all. If it does, go back, take your time, make sure it makes sense. But at this stage, I'm going to carry on as if this makes perfect sense to everybody, because this is the way it works. Any questions before I move on, though? This is your last chance.
Would it be a fair way of thinking of it then, that like any variable that's in reference to a list, any change for that variable would change any other variable kind of referencing that same?
No, because if you change the variable, you can change the variable all you want. If you change the list, if you change the thing that's referenced,
then that's changing all.
but it's not changing all the references. All the references are left alone. You're looking to connect some dots. You're making it more complex than you need to. The good news is it's simpler. Everyone in here, imagine you're looking at a car, and I open the door, and all of you are going to say, oh, the door's open now. But I didn't modify all of the references. No, I just modified the one car. Everyone observing that car observes the car change. But nothing about those references changed. The car did. I modify the list. Everything observing that list, all references to that list, they're not changed. The list is changed. The references still reference that one list. So I know what you're trying to do, but you're actively working too hard. Stop trying to be a good programmer and just be a good programmer. Right? That's the trick. Remember, programmers are stupid. If you overcomplicate things, it's a recipe for disaster. Keep it simple. That's all that's happening here. When we have a situation like this, we call these reference variables aliases. It's like you have another name for that one thing. But again, really, it's not that one thing. You have these separate names that all reference the same one thing. Now, given this whole reference thing, look at this function here, add to list. This function doesn't return anything. I mean, it does, it returns none. But it's not returning anything we care about. Take a moment, look at this code. On line 4, we create a list. Okay? And the reference variable A-list is a reference to that list. On line 5, I call the function add to list. And the argument this function gets is a reference to a list, not a list. So if we go and look at the parameter there, some list, with this chunk of code right here, this 6 lines, the variable A-list and the parameter SUMList are aliases for the same one single list. When you pass a reference variable as an argument to a function, it doesn't make a copy of the list. It leaves the list alone. You just passed a reference to it. This is an example of a function that has a side effect. Pure functions in mathematics and computer science are functions that, like, they map arguments to some value. Remember in like grade 10, learning about functions? Remember you learned about like range and domain? Remember learning about that in grade 10? I think it was grade 10 for me. It was a while ago now. So you should have a better memory than me. And remember, you weren't allowed to have multiple like x values mapped to the same y value. That was against the rules. Right? So, I mean, that's a function, right? Functions map some input to some output, some arguments to some result. Here, this function doesn't map anything to anything. This function takes a reference to a list of value, and it doesn't return anything, but it did modify something somewhere. It modified the list that it had reference to. This function has a side effect. It's an impure function. Impure functions are not intrinsically bad. They're not bad, but they often are the root cause of a lot of issues. So they're not bad in and of themselves, but they're notoriously known for causing issues down the line, which is a problem. And if you think to yourself, well, with my code, I really need to have an impure function here. I need a function that needs a side effect because I just can't do it any other way. You're wrong. You can. It might require you to refactor some of your code, go back and rewrite some of it, because it might be possible that you've kind of coded yourself into a corner where you're kind of stuck and have no other alternative. But maybe the right thing to do is to backtrack a little bit, rewrite some of your code, think how you wrote things, and modify it a bit. You're new programmers, but refactoring code, which is just a fancy word to say like, okay, you've got working code, but maybe I can go and change it, improve it a little bit. That right there, that's a big part of programming, huge part. If you are writing your code on an assignment and you get it working, and you have this like you're reluctant to go and modify any of your code that's already working. Don't get me wrong, I get it, but that's kind of the wrong attitude. You're going and refactoring your code is a good thing. That's a good, very good thing. You improve your code. That's not just renaming variables. That might be like just cleaning it up and just changing how things are done. But so this right here, an impure function with a side effect. This function doesn't return anything. And there's nothing wrong with that. But this function modified the value. It modified a list somewhere else in your program. That list was stored somewhere in RAM. And this function modified it. It didn't return anything, though. So this function, it's impure. Now, we can... So yeah, this is just... Yeah. We can change it. We can effectively do the same thing as I did before, but eliminate the side effect. So here's what I'm doing. Add to list. It takes a reference to a list and the value. It makes a copy of the list. So it leaves the list it got as a parameter, although it never really got a list as a parameter. It got a reference to a list. But it leaves the list that we wanted it to start from. It leaves it alone. It makes a copy, and then it modifies the copy and returns the copy. So now you've got a function that doesn't screw around with the arguments. It leaves the arguments alone, and it produces a new list. And then if you say to yourself, I'm just going to copy this code and I'm going to show you what I would say. Or if you were to say to me, well, no, I get it. You're saying, make a copy, modify the copy. But what if after all this I really wanted a list, the reference variable a list, to be the modified one? Fine, do this then. Other list doesn't exist anymore because we obliterated it. But we took a list, we passed it, we left it alone, but then we replaced what a list referenced with the new one. So now you're doing the same thing as before with no side effect. This is a lot easier to test. It's a lot easier to reason about what your code's doing. It's really hard to keep track. Look, I look at this code, I see arguments, and if I know the arguments are left alone, and I see a return value, which you can't see because of the pop-up window, I know what to look for in my code about what's been modified. But suddenly, if I am modifying values somewhere else in my code via reference variables, it's a hell of a lot harder to keep track of what the hell's going on in my program. It becomes a lot more complicated. You've got all these things connected. It's too much. It's easier to keep everything, your functions, nice, pure, independent. They're easy to test, easy to reason about. You're in good shape. This hedges against a lot of issues. Remember how raise your hand. I think I may have asked this on Friday, but I'm going to ask it again anyways. Raise your hand if you've been working on assignment 2. Raise your hand if in the infect city function, you wrote it, and be honest, you wrote it, and 2/3 of the tests pass. But those last 2 little tests, those last 2 assert tests fail. The ones that say not new city is old city. Did anyone have those tests fail but every other test pass? One person? Everyone else apparently got it right, even though the other section had a very different answer. That's because your function had a side effect. It's because your function modified the city, the list, that it got referenced to for an argument. The trick is to make a copy of that city and modify the copy. And then suddenly you're fine. Because the is operator doesn't check equality. The is operator checks if you have aliases. It checks if you have 2 reference variables referencing the same thing. If you have 2 reference variables referencing the same thing, obviously they're equal. But let me show you what I mean here. Both are true. I have A is a list, B is a copy, A is not a list, A is a reference to a list, B is a copy of the reference to that list. So the first question I ask is A equivalent to B? Yes, they are equal. Then I say, is A is B? It checks, are they literally referencing the same thing? And it's true. If, on the other hand, I were to do this, now I get a different result. I have two lists that are equivalent, but they're not, A is not literally the same list as B. This is a very important thing, very different. Any questions about this? I'm seeing blank faces, and I don't know if that's because you're like, yeah, obviously, or if it's because you're so lost.
Would A dot copy do the same thing?
Yes, it would, yeah. Or you could slice the whole thing, but I don't like that as much because to me, this is a little bit more clear. And part of what I consider more clear is this right here. There's a lot of very similar programming languages. Java, C, C#, C++, Python, JavaScript, they're all very similar. Their syntax is very similar. But this right here, this slicing thing, that index colon, that's a very Python-y thing. That's a Pythonism. And so if you're a Python programmer, you look at that, you know what it is, whatever. But let's say I'm like a 20-year veteran of Java. I come along and I see that and I go, what the hell is that? There's no reason there's no reason a Java programmer would know what that means. A Java programmer sees that, they go, oh, okay, it's probably making a copy. The code is a hell of a lot more self-explanatory. So it's a little nicer that way. So yeah. I'm forgetting something I wanted to hit. Anyways. Now here's something I want to emphasize here. What do you think here? All right, so first of all, let's reiterate the whole making a copy of a reference. This is my list, okay? I make a variable A, and A is a reference to the list, which I'm representing as that arrow. Trust me, that's an arrow. Let's try that again. There, right? So A is a reference. It's not a list. When I come along and I say B equals A, Python goes, oh, I'll make a new variable called B, different color, and copy over the contents of A. And what is A? Is it a list? No, of course not. What a silly comment by me. So I make a copy of the contents of A, which is the arrow. I'm representing the reference as the arrow. Right? So, there. That's what happens. And if I say A at index 1, you become X, suddenly B goes, oh my God, that one single list that exists has been modified. The trick was to go make a copy of this and then have B reference the copy. And then we were good if this is what we wanted to happen. People at this stage start to think like, well, how am I supposed to know which one I want? Well, what do you want to do? If you want to make a copy of a list, you make a copy of a list. If you want to copy the reference, you only have one list, you want to have a copy, well then you do that. Now, remember I made that whole stink about strings being immutable, right? I can't go and modify a string. And then if you say, but I really want to, I say you can't. And you say, what if I really, really, really want to? I say, you can't. You can't do it. What you could do is make a new string based on the old string with the changes you want, but you can't modify that string. By making your lists, if I make that append to list function, the pure version, the one where it doesn't modify the original, I have a function that doesn't modify the original. Ugh. If I have a situation like this, and I have a list, and the list is mutable, and I show up and what's going on here? Weird. What? I don't know what's happening, but Paint's freaking out. All right, let's clean this up a little bit more. Try to clean it up a bit. If I do this, and someone comes along and does this, they modify that list some way. That's me modifying the list. And I wasn't expecting this to happen. And I have multiple references to that one list, and that one list gets changed somehow because that list is mutable. We can change it. If I modify it, and I really wasn't expecting it to happen, both references to that list are now messed up. They all get out of whack. But by making our function pure, by making it so, let's pretend this is a string. If it's a string, I could have a billion references to that one string, but I can't modify it, meaning this issue of one reference variable modifying that string and then screwing it up for all the other reference variables can never happen. It's impossible. The string's immutable. You can't change it. If you really want to change it, make a copy. But with lists, they're mutable. So you can do this, and it messes it up for everybody. Maybe you really wanted to do this, maybe, or maybe you messed up, which is likely the case. And suddenly, yeah, you can introduce a lot of bugs like this. And these bugs are very hard to debug. They're hard to track down, and they're hard to resolve. It's better to eliminate these bugs before we start by pretending your lists are immutable. Make a copy and don't change it. If I have a function, add to list, that does not modify the original list, but makes a copy, I'm pretending the list is immutable, meaning this bug can never happen to begin with, which is really good. You might say, well, hold on though. I have a list here. If I have one list, and every time I want to make a change to it, maybe I want to make a change to it like 100 times in my code. I need to make a copy. I need to make 100 copies. Isn't that like kind of inefficient in your code? It is, but it's not 1982, and that doesn't matter. It really doesn't matter. Unless you're really worried about like some very specific, maybe some embedded systems where you're dealing with some really like shitty processors, or maybe you're like really concerned about performance because it's like a video game engine or something, then there's arguments there. But when you're simulating a zombie apocalypse, it doesn't matter. And I'm not saying that to trivialize the work you're doing. I'm saying that that's because that's like 99.9% of the work that's being done. That type of stuff doesn't matter so much. And on top of it, there is when you write your code and you hit run, the code you wrote isn't what's actually run. There's software that will take your code and turn it into the low voltages and high voltages that can actually run on your computer. But in the process of doing it, those pieces of software that does that translation will also go like, we can improve this a little bit. It'll actually like optimize your code with you not even needing to know it. And I've said this before, and I'm going to say it again, because maybe now at this point in the semester, it's going to become a little more clear with an example of something like this. Computer code isn't for computers. It's not. It's for other humans. It's for humans. Machine language, the zeros and ones that actually get run through your computer, that's for computers. We have software that does the translation for you. So when you're writing code, make sure it's written in a clear way such that it is for other humans. Write your code in a way that's clear and easy to understand for humans, and let the compilers, let the optimizers do the optimizing. You don't need to worry too much. They do experiments every once in a while, because you get these like hardcore geeks that'll be like, no, I'm better, I like to optimize my code way better, blah, blah. And they can't beat the optimizers. You can't beat the software that optimizes because of the hacks and whatnot it does. And these optimizers are built for specific processor architectures and everything. It's nuts. You're not going to beat it. And if those weirdos that dedicate their lives to thinking that they can out-optimize an optimizer can't do it, you really don't need to worry. Maybe one day you could do it, maybe. Probably not today. So don't worry about it. I'm not telling you this for any other reason than keep it simple for yourself. Write good, clean code that's for humans, and you're in great shape. Now, let's say, I'm going to start over because something weird happened with this one. I've got a list. Let's say I have a situation like this. Now, what is inside my list? Who said references to lists? Because you're absolutely, yes. If you say, oh, it's a list of lists, I go, no, absolutely not. It's a list of references to lists. So when I say A equals that, what I say is, okay, I have A, that's a reference to a list that contains references to other lists. So if I were to draw this, really what I have, and I'm going to draw these sublists, it's like a different color. Nope. Right? Does this picture make sense? No. You were one person responded and you went, no. So I have A. Let's go here. And here, let me do comma, comma. A is a reference to this list, and this list contains 3 elements. I'm gonna redraw this. I'm gonna visually write it out like that to hopefully help. This list contains 3 elements. A references a list that contains 3 elements. Each of those elements is a reference to a list. So we have A, it's a reference to the outside list, that's the green one. And inside we have references to those internal lists. Give me a thumbs up if you're happy. A lot of people didn't give a thumbs up though, so I don't know. It was hidden. I see it. It was obscured. Okay, so you're good. Now if I say B equals A, I do this, right? Then I've created an alias. Okay. Now, true, true. But no, what I want to do now is I want to say copy. They're equal, but is A equal to B? No, because I made a copy of it. But can anyone look at this picture and have a follow-up question to these two questions I asked right here? If I made a copy of A, what did I copy over? Yeah. What I want to know is A at index 0 is a reference to this list, the list AB. When I made a copy of A, what happened here? Based on this right here, let's draw what happened. So I made a copy of the outside list A, like that. Okay. And I didn't make copies of these, no. I made copies of the references. So, are A and B equivalent? Yeah. A is B? No. Nope, not at all. They reference two different lists. But A at index 0, which is a reference to this list, is the same as B at index 0 because it's a reference to that exact same list. And if it wasn't obvious, we could play this game forever. Where what if A is a reference to a list that contains references to lists that contains references to lists that contains references to lists, etc., etc., etc. Just the lists and no, nothing more than what you just said. You might be thinking of recursion, but that's not quite the same thing. Do you know what it is? A matrix? Ah, okay, yeah. So that you could think of it like that, but really it's not though, because it would be a list of references to other lists that we could pretend is like a matrix or a two-dimensional list. But really it's not. But often programmers like to think of them as matrices or lists of lists, or two-dimensional lists for simplicity. But at the back of our mind, we all know what really is happening, and that's the important thing. And assignment 3 is all about this, by the way. But if you're paying attention and this makes sense, you're in great shape. It's going to be a joke. So, what do we do about this situation? Well, there's fortunately a rather simple solution. When I did this copy here, it did what we call a shallow copy. Now, first and foremost, this whole shallow versus deep copy isn't going to matter if you pretend your data is immutable. If you just pretend everything's immutable and you can't modify it, it doesn't matter how deep or shallow your copies are. It doesn't matter. Because you can't modify it anyway, so who cares? But if you're depending on it being mutable, and I say A at index 0 equals X, print A, print B, we see, well, they're both modified. Like, but I just made a copy, not of the internal thing, so you're in big trouble. Now, if you're expecting it to be immutable, then it won't matter. But let's say it really matters. So what you do is what we call a deep copy. A shallow copy is you copy over this thing, and then a deep copy is you go all the way down. And then if you say, well, what if I only want to go halfway down? I say, well, then have fun. So you do what's called a deep copy instead. And fortunately, there's an easy way to do it. Now, there's no deep copy method built into lists, but you can import the copy library. And within copy, first of all, you can actually just say copy dot copy. You can use the copy method, and it will work just fine. Let me get rid of these two. This doesn't matter anymore. Right. You don't need to use the method. There's also a copy function that does it too, but they do the same thing. But within the copy, there's also something called a deep copy. And that will solve the problem, if it matters. Now, if you're thinking, oh, this is perfect, this is going to solve my issue on assignment 2. No, it's not. Just, you don't need a deep copy. You're fine. I mean, if you want to use it, go ahead, but you don't need it. Chances are, if you think you need it, and if you do, you're again, classic new programmer mistake. You're making it way harder than you need to. Any questions about all this stuff? All right. All right. Now let's just blitz some string or list trivia. So, a list. Again, the point of me showing you, just like with the strings, the point of me showing you this list trivia is not that you're going to memorize all this and you're good to go. This is not exhaustive in any way either. I'm just showing you a bunch of things that you can kind of think about, and if later you need to know it, you can look it up. It's better to know what you don't know than it is to not know what you don't know. Because if you know what you don't know, you can look it up later and learn. If you don't know what you don't know, what are you going to do? So, you can get the length of a list, just like you could with a string. You can have an empty list. You can print it out. You know, it renders as like the little square brackets. You can ask its type. It's a list, but it'll have a length of 0 if it's empty, just like a string will be length 0 if it's empty. You can have lists inside of lists, although not really, because really you have lists of references to other lists, but like what they were asking, we often think of them as lists of lists just for ease in our heads, but while being very aware that that's really not what's happening. You can append. You can append something to a list if you need to. What do you call that type of, what is append? What do we call that? There's a special word we use for something like that. Method. A method. It's not a function, even though it totally basically is, but it's not. It's a method, which is a function that acts on an instance of something of that type. So this is a list. Some list is a list. And when I called append, it's appending to the implicit argument, which is the list it was called on. Yeah?
Or is there a way you can append between a list, like if you wanted 90?
Yeah. You can, and I can't quite remember what it is, but let's see if we can figure out real quick. So A dot So append, see if append gives us an option to the end. There might be like something like insert. Yeah, there we go. Insert, I don't know, x. I don't know how it works. I'm just going to try this. No, 9's not going to make any sense. 2. No. Okay, maybe it needs to go 2 with an x. There. There. 0, 1, 2. At index 2, I added an x. There. There's a lot. If you ever want to know, what else could I do? You can go look up the docs, or you can do what I do, which is, all right, well, I can insert, I can index, copy, clear, count, extend, pop, remove, reverse. And if you ever want to know, you just hit like tab, and like give it a second, then the doc string will actually show up. This is the doc string that someone wrote for this method. And it tells you how it works. Yeah. You can concatenate lists like this. Now, mind you, list A and list B are left alone. When you concatenate two lists, it creates a new, bigger list, but the original two are left alone. So you can concatenate just like you did with strings. You can repeat them just like you did with strings. And Python actually has some built-in methods. Now, what's neat here is, like if I said, you know, max is a function that can take like an arbitrary number of arguments that will then tell you which one's the biggest, right? Obviously, if I'm doing this with literals, it's rather silly. But imagine I was reading an input or something and I needed to know which one was the biggest. But what's cool about this is I could have the list. Excuse me. And it'll work on a list as well. You can sum it. Even, obviously, this is a bad name, the sum. You can sum those. Now, if I were to write a function, def or maybe it's a float because you never know. Right, here's a function I wrote really quick that will just sum up the contents of some list. Python has a function that already, like for free, that does it. How different do you think Python's functions algorithm is versus my functions algorithm for summing up the contents of a list is? Do you think it's very different, or do you think it's basically the same? Probably pretty close. Yeah, it's going to be the same. Look at each thing and add it to some running total. That's all it's going to be. And at this stage of the semester, I'm not saying that you should have been able to get this like that, but if I asked you to do this in a lab, this should be something that you find relatively easy. And if you didn't, it's probably because you were trying to make it harder than it is. But the point is, you know, Python gives you these built-in functions for free, and you could write those functions yourselves at this stage really easy. Some of the mystery, like that veil of Python's magic is disappearing once you kind of know enough of how to do things on your own, that suddenly you realize the fact that it gave it to you for free just was a minor convenience. Good, but it wasn't doing something way too hard or complex for you. If I gave Python's list, if I gave that sum function a list of 1,000 things, how many things does it have to add up? All of them, 1,000. If I gave mine a list of 1,000 things, how much does it have to add up? 1,000. If I double it, how much do you have to add up? 2,000. You double it. Again, this is an example of a linear time algorithm. Now, when I say that, I want to be very clear. I don't quite mean that the total amount of work it does is linear based on the input size, the input being the size of that list. That's not quite what I mean. There's a nuanced difference. What I really mean is the amount of work this function has to do grows linearly as the size of the input grows. If I double the input size, I have to do like twice the amount of work I would have done before. So it's not the amount of work that's happening in the function. I mean, it is, but really it's more about how much the amount of work changes as I change the input size. And the change is linear. There's a nuanced difference that's important, but this is something that we talk about a lot more a little later. There's a lot of things built into Python that hide some of the work for you, but that work still happens. So if you think to yourself, oh, I had to write the code and I have to loop over all the contents, right? But if I use the built-in sum function, I don't need to loop over all the contents. Well, you didn't need to, but the computer still did. So you're really not saving any steps. Any questions about any of that? All right, cool. All right, we'll pick up here tomorrow.